which is one of the important and practically used line coding scheme, which is known as Manchester coding. This is sometimes known as split phase coding as well. Okay, since I've not drawn any waveform for this, I'll first write what is the scheme involved in converting your bits into pulses. The scheme here is S of t, okay, is plus a for only half duration of time and minus a for another half duration of bit period for bit 1 itself. And for bit 0, okay, if I say this as S1 of t, and for bit 0, S2 of t is reverse of it, minus S1 of t for bit 0. This is an interesting scheme where there is a transition for the same bit in between. There is, for half the duration, it is, 0 degrees. For another half of the period, it is shifted by, another phase, a 90-degree phase shift. And hence, there is a split of phases for same, bit representation. Okay. So by representation, I can say, I can represent bit 1 as, okay, so if this is a time scale, I can represent this as, this is for half the duration, this is plus a, and for another half of the duration, this is minus a. This is 0, this is TB over 2, and this is TB. Okay, so of course this is magnitude is plus a and minus a. Okay, it's a biphase coding, sometimes known as biphase coding also, or split phase coding, and famously it is known as Manchester coding. We'll talk about more about that. And bit 0 is represented exactly opposite of it. For bit 0, it is exactly the reverse of it.
Return to 0 or non-return to 0 scheme, sir?
Yeah, this actually cannot be told as return to 0 or non-return to 0, because this is splitting its phase in between. It is returning to 0 by its scheme logic itself. There cannot be non-return to 0 for this, because it is changing in its phase in between. If it was non-return to 0, it should have got constant amplitude for the entire duration. But the logic doesn't involve with respect to any return to 0 or non-return to 0. Hope you understand that a difficulty in understanding this Manchester coding. Correct. So I cannot have non-return to 0 scheme at all, because I intentionally am changing its amplitude in between the bit duration. Okay, and hence Manchester coding doesn't fall under any category of either return to 0 or non-return to 0. It's completely different. So minus a and plus a as with respect to 0 to TB by 2 and TB. Okay, so let's try to analyze this type of line coding. What could be the advantage or what could be the disadvantage of such scheme that I have taken now. Again, we'll try to calculate power spectral density. For that, I'll try to calculate the autocorrelation function, which is interesting. Let's first find out what is autocorrelation function. Okay, so similarly for previous cases, I'll first take for k is equal to 0. So for k is equal to 0, r of 0. So again, there are two pulses, S1 and S2. One is the combination of, it can be 1, 1 and 0, 0 for k is equal to 0. Okay, so and hence if these are equiprobable, the probability between them is again split into half ways, so that this is half times please carefully note for this part, this part of calculation of autocorrelation function. Since I take 1 1 combination, say bit 1 and 1 for k is equal to 0, and bit 0 0 is a combination that can have for other case. Okay, so for bit 1 and 1, it's multiplication of the same signal with itself. Okay, and again this is half of the probability, I mean half the duration of bit period is positive, and for another half of the bit duration it is minus half. In for combination of bit 1 and 1 itself, again it is further subdivided into equiprobable case. In other words, I write this as half of, it is a into a and half of minus a into minus a. Okay, so this is for combination bit 1 and 1. Similarly, for bit 0 0, I have got again this half in the outside the braces is with respect to the combinations 1 1 and 0 0. There could be only two combinations for k is equal to 0, and inner scalars half and half is with respect to the changing of the pulses, changing of the phases in between the bit duration. And similarly, for the combination of 0 0, I will have the exactly opposite of it, say half minus a into minus a, correct? So plus half into a and a. Okay, so this will result in what will the result of this? This is a square by 2 plus a square by 2. This is a square by 4. Similarly is for the second half as well. So this is a square by 4 times 2, which is a square by 2. Okay, so this is for the case k is equal to 0. So for all other values, okay, so for k not equal to 0, r of k, okay, this can be calculated in this fashion. So what could be how many combinations? As we know, there could be 4 combinations because there are 2 pulses, s1 and s2. Okay, so I'll write them first as generic formula, an times an plus k times pi. Since there are 4 combinations, if they are equiprobable, occurrence of those combinations are equiprobable, so the probability is 1 over 4. Okay, so 1 over 4 times, say first combination I'll take it as 1 1. Say 1 1 combinations we have already calculated in this fashion. I'll write for first case. Okay, so this is a into a plus half minus a into minus a. Okay, so this is combination 1 1 plus 1 by 4 times 1 0. Say for the bit combination 1 0, how will it be? Say if I want to multiply bit 1 and bit 0, I'll be multiplying s1 and s2, right? So with that, s1 and s2 are exactly opposite of each other, so this will go as a into minus a plus half of the other way around, minus a into plus a. Okay, so with that I can have the combination of 1 0, and for the other combination I'll complete this properly so that you'll have complete idea. Say for combination of 0 1, this is half of minus a into a, the exactly opposite of this, plus half of a into minus a. Okay, this is for 0 1, and finally for 0 0 we have already written that, but to exclusively write that, minus a into minus a plus half of a into a. Okay, so this is for combination 0 and 0. So what will this result in? Okay, if you check this properly, okay, if you check this properly, I'll write that a square by 2, a square by 2, and hence this is 1 over 4, the first will result in a square. The first combination will result in a square. The second combination will result in what? Minus a square, minus a square, and hence this is minus a square by 2 times 2, which is minus a square. And for the third combination, it's exactly the same way. And for the last combination we have got is plus a square. Again, this will result in simply 0. So autocorrelation function for k not equal to 0 will also result in 0. Right, so that r of k, the autocorrelation function, will exist for only k is equal to 0. Value is exactly similar with bipolar NRZ scheme. And we need to calculate g of f as well. So g of f is not a simple rectangular function. I cannot say it is g of t is rectangular t over tb. We need to calculate this g of f now. So I'll begin with representing this in time domain. Okay, first I will take this as a rectangular function, okay, which is running over for tb by 2 duration, because half of the bit duration is positive and other half is negative. So this for 1/2 of the duration. In other words, this is tb over 2. Okay, this is for 1/2 the duration, which I can represent as this function. I can represent mathematically as a rectangular function. Okay, this is nothing but t over tb by 2. Okay, I'll represent in this fashion. Okay, so this is the rectangular t over tb by 2. Okay, so to the total entire duration of the signal is tb over 2. And what we have as g of t now as Manchester coding for bit 1, say this is my s1 of t, where this is actually is the center. So we have for half the duration is negative, for other half it is positive. This is tb by 2. This is minus tb by 2. So total duration is tb. Okay, so the transition is at exactly at 0. So we have got this point as tb by 4 and tb by 4, which I have represented earlier. All right, so this is nothing but this is a rectangular pulse, rectangular of t over tb by 2, shifted left and shifted right. Correct. So if I say this as, carefully note these points, this is plus tb over 4 and this is minus tb by 4, right? It's the same pulse. This is at t is equal to 0, is exactly the same pulse, but shifted left by minus tb by 4 plus shifted right by plus tb by 4. Correct. It's a combination of two such rectangular pulses, but so those two rectangular functions are shifted, one left and another as right, and hence I can write this g of t as, okay, so therefore this is g of t. If I say this as g of t now, this is a representation of binary 0. I can do it for binary 1 as well, exactly similar to that. Okay, so both are similar to each other. So one example I have taken here. So g of t is now nothing but it's a rectangular function, okay, t over tb by 2, but one is shifted left. Shifted left, I represent this as t plus tb by 4 over tb by 2. Okay, so this is my left part, and the right part is, it's a rectangular function shifted right, which is t minus tb by 4 over TB by 2. Okay, so our job is to find out, remember, power spectral density, for which I need to find out G of f, and hence Fourier transform of, okay, of this G of t is nothing but, okay, as we know, for a transform of rectangular t over tb by 2 is a sinc function with an amplitude of tb. Now this is time shifted version of the same rectangular function. So with utilizing the time shifting property of Fourier transform, I can write g of f as amplitude is tb over 2, okay, because I know that, okay, please make sure that you know this relation. I have written that already, but just for the sake of clarity, if g of t is a rectangular t over tb, its Fourier pair g of f is tb times sinc of pi of tb. Okay, so with known that fact, I need to calculate Fourier transform of this combination now. So this is tb by 2 times sinc of, okay, sinc of pi f tb over 2, okay, and I know that by time shifting of the function will result in frequency domain into exponential part, which is j omega tb by 4. Okay, so this is the first part. The second part is similar to this, which is tb over 2 sinc of same function pi of tb over 2 into e power minus j omega tb by 4. Okay, so finally I can simplify this as tb, sinc function is common, which is tb over 2 sinc of pi ftb over 2. What I am left with is exponential part and addition of these two exponential. The one is complex conjugate of each other. Okay, that I know. This is the using Euler's identity. This is nothing but j sine theta. I'll get back to the actual advantages and importance of this Manchester coding, because one of the practical schemes Manchester coding is used in your Ethernet LAN cables. I wanted to elaborate on that, but anyway, I'll just continue with method analytical part, and I'll pick up the explanation part in the next class. Okay, since it's a combination of opposite rectangular pulses, I had written it as positive. Now since it's a combination of opposite amplitudes of this rectangular pulse itself, I have just changed, modified this addition of these two rectangular pulses into the difference of those. So just with the completion of this expression, we know that difference of this exponential is nothing but j sine theta, e power j theta minus e power minus j theta, that we know is j sine theta, which is the final expression of this j times tb over 2 sinc of pi f tb over 2 into sine of 2 pi, I mean omega tb by 4. Omega I can write it as 2 pi f, so 2 pi f tb by 4. Okay, so this is g of f. My job is to find out power spectral density. So therefore I'll just write this expression and conclude this session. The PSD of Manchester NRZ, I can say Manchester coding scheme, okay, is SS of F is nothing but using that Wiener-Khinchin discrete form of Wiener-Khinchin theorem. Okay, SS of F is simply a magnitude of this whole square over TB. Magnitude is nothing but, there is J in the term involved here, and hence the magnitude of this of will be simply A square TB times sinc square pi F TB over 2 times sine square pi F TB over 2. Okay, so this is a final expression for power spectral density, as autocorrelation function exists only for k is equal to 0 with an amplitude of a square, which I've corrected. So for any other value of k, the autocorrelation function is 0, and hence there is no summation part, unlike your unipolar NRZ. Okay, so we'll try to list out. Now I will try to analyze this expression and list out advantages and drawbacks of this Manchester coding. But with respect to the earlier two cases, it has got plenty of advantages and practical implications as well. So we are in the process of finding out characteristics or attributes of several line coding schemes. We completed two of them. One was unipolar NRZ and polar NRZ, and I was discussing one of the important line coding scheme which I had not listed in the session, where there were a few varieties of line coding schemes. So one of them is Manchester coding. It's also called as split phase coding. The reason for it to be called as split phase coding, because it has transitions in between the bit duration. So for bit 1, if it goes for half of the duration for plus a, another half of the duration it is minus a, and for bit 0 it is exactly opposite way. You can have the other way around as well. You can have bit 0 as s1 of t, and s2 of t can be assigned for bit 1. Nevertheless, the performance of this type of line coding scheme will remain the same. So we started off with calculating power spectral density. We calculated autocorrelation. Autocorrelation will be a square for k is equal to 0, and for all other values of k, autocorrelation function is 0. And to calculate g of f, we took we defined a rectangular function of this nature of duration tb by 2, and either bit 1 or bit 0 can be regarded as the difference of two such rectangular pulses, shifted one left and shifted another as right. Okay, so with that we tried to calculate power spectral density using Fourier transform, and finally we arrived at this expression. So our job is to list a few properties and advantages or disadvantages of this kind of line coding scheme. So first I'll list disadvantages, then I'll talk about the pros of this. Okay, the drawbacks or the cons of this scheme is with respect to the bandwidth. Bandwidth is larger compared with other two codes that we studied with unipolar or bipolar or simply polar, a polar non-return to zero coding scheme. Okay, so it's obvious that there is a function of sinc square pi of tb by 2, and hence the power spectrum density is governed by its amplitude by nature. Of course, it's multiplied with sine square as well. Okay, but the magnitude is majorly governed by sinc square function. For the positive, it goes with the diminishing amplitudes, and it has got nulls or zeros at every 1 over tb by 2, 1 over TV by 2 can be written as 2 over TV. Okay, and this will be twice of TV by 2, so this will be 4 over TV, and so on. Okay, so majority of the content of the power spectrum density will be occupied within the bandwidth of 2 over TB, and hence this bandwidth is actually twice of the bandwidth that we had seen for unipolar or polar NRZ. So compared to those schemes, the bandwidth is double than those schemes. Okay, so that's one of the drawbacks. Second is with respect to error detection. Again, there is no error detection capability. Okay, so there is no error detection capability where if bit 1 is if bit 1 is flipped as bit 0 during the transmission, the receiver cannot understand the error, so it will just decode it as as an erroneous output itself. Okay, so there is no error detection capability at all. But with respect to advantages, these disadvantages are very small. Okay, so we need to talk much about the pros of this Manchester coding scheme. Okay, the first and important part with respect to unipolar and polar coding, we had the problem of uh, in fact this is not the exact uh, spectrum that I should be talking about. Okay, this is a spectrum for sync square. Okay, not for this. Okay, remember pi of TV by 2. Okay, this is a spectrum or frequency spectrum for the term of sync square, not for the entire power spectrum. So since there is sine square term, as you can see, if I try to find out the value at f is equal to 0, because that was the major drawback of polar and unipolar NRZ scheme, where there was a finite or non-zero power content at DC, or f is equal to 0 value. As you can see from this expression, at f is equal to 0, of course sync square is a non-zero function, but it is multiplied with another function which is in terms of sine. So we know that at f is equal to 0, sine of theta is 0 itself, and hence we can see that. I'll try to draw the complete spectrum once I list off all the line coding schemes. Then we'll try to compare each one of them. But as of now, I can say that at f is equal to 0, or for DC values, power spectrum has no value. Okay, and hence this is one of the advantages when you compare with other schemes. So we don't want any power to be dissipated at DC, which is simply, as I said, it will heat up the circuit. So and hence this is one of the major advantages of Manchester coding, and we have overcome it. Okay, and the second important part of advantage is about timing. Okay, timing is always available. We'll talk a little more about this. Or its Manchester coding is known for self synchronization, and hence, okay, and hence it poses no problems for long strings of zeros. Okay, so if there is a long strings of zeros, there's a problem with polar and unipolar NRZ schemes or RZ schemes, where there was synchronization between transmitter and receiver was lost if there was long strings of zeros transmitted from the transmitter end. Okay, but in Manchester coding, that problem is not there. Why? Okay, we'll try to explain that. Because of few good reasons. Because there is you know a good synchronization. What I mean by this good synchronization is that it's easy to get timing signal or clock signal. Okay, timing signal or clock, okay, from the coding waveform itself. Okay, because of the fact that there are transitions for both bit 0 and bit 1. Okay, there are transitions, as you have known that it's a split phase coding. So for both of the bits representation, we have used transition in between the bit at exactly at midpoint for 50% duration. So there are transitions for both 0 and 1 at midpoint of a period. Okay, even if there is a long strings of zeros, the receiver will still be getting certain phase reversals. I mean, there will be certain finite amplitudes or finite waveforms that would be received by the receiver. Okay, other cases for polar or unipolar NRZ schemes, even for polar, I can say that even if there is a long list of long strings of zeros, you would have sent minus a p of t, or the amplitude of pulse waveforms was minus a in the amplitude. However, if there is any error in the channel of the transmission, then you may you may say that bit 1 probably bit 0 probably flipped into bit 1, or simply there was no signal at all. But in case of Manchester coding, even if there is any error, definitely you may find transitions in between the waveforms, because if bit 0 is corrupted to be bit 1, again there will be a transition, or if bit 1 is corrupted to be bit 0, there could be a transition. Unlike in the cases of other line coding schemes that we have studied, you have information about these transmissions, or the samples are taken at the proper intervals of time, and hence there is a transition in between the period which serves as a synchronization part. So this kind of schemes which are actually very famous in early of 1940s and 50s. So these were first introduced with actually magnetic disk drives. Okay, whatever hard disk drive that you find in our personal systems, so these were introduced in such of magnetic disk drives. Okay, so where in this there was a requirement of read heads, where the header of the magnetic disk which reads the data, where these were only sensitive to transitions. Okay, so these read heads were just sensitive to only transitions which were governed by magnetization. Okay, and the Manchester coding actually guarantees, okay, at least one transition per bit. Okay, because there is a transition for both bit 0 and bit 1, so it guarantees at least one transition per bit, and hence the read heads were able to detect the data written over those magnetic disk drives. Okay, as I told, the transition in between the bit periods is helpful in keeping the timing or clock information intact. So this was first introduced actually by G.E. Thomas. Okay, these kind of coding schemes were introduced by a scientist known as G.E. Thomas. Then later these were improved by another scientist known as Andy Tenenbaum. Okay, so he is one of the famous author of your computer communication network course, which you will be studying in your next semester, by written by Andy Tenenbaum himself, and later been revised by several other authors. But he was the one who was known for improvement of this Manchester coding, and hence there was a significant contribution from his side. Okay, so this is the origin of this kind of line coding scheme. Currently, this is widely used in your wired Ethernet or WLANs. Okay, so this is with respect to the standard IEEE 802.3. Okay, and also in some cases of low power near field RF devices, okay, which use a technology of NFC, near field communication. So even those device make use of such kind of coding scheme, because actually you can extract the clock signal using any good receiving techniques such as PLL. Okay, so you can extract, in fact, you can extract the clock signal, okay, using digital PLL. You need not send the clock signal separately. The data itself will consist of clock signal at which the transition occurs, which is the half of the period of the entire bit duration itself, and hence this serves indirectly as a phenomenon of clock extraction at the receiver end. Okay, so this digital PL in fact demands high density of uh, bit transition, which your Manchester coding serves. It demands a high density of bit transitions. Then only uh, you'll be able to detect what is being transmitted from the transmitter end. So much and so about about Manchester coding. As far as the last advantage of this, except with respect to error rate, the error rate performance, okay, is similar to your other schemes. Is same as, I can say, as bipolar. Okay, bipolar NRZ schemes. We will calculate all these error performances along with channel coding schemes. As I told you, these pulses will again, these line coding waveforms will again be modulated using channel coding schemes, which we will be dealing in your next semester in CS2 course. Again, we will take all these line coding schemes and try to find out what is the probability of error, or will evaluate the error rate performances of all these line coding schemes in your CS2 course. As of now, we'll just say that the error rate performance conceptually, or just as a statement that for polar and unipolar, sorry, for bipolar NRZ, the error rate performance is similar for the Manchester line coding scheme as well.